In this video, we are going to be focusing on chapter number 19, which is transition elements and their coordination compounds. This part of the video, which is just video 1 for this chapter, will majorly focus on what are transition elements, what are their properties, and how do we write their electronic configuration. Okay, so let's begin. So this is the general look of how a periodic table looks like, right? So I'm hoping you guys remember this from your previous course, Chem 100 or Chem 101, that in a periodic table, these elements that you see right here, these groups, the first two groups, group 1A, group 2A, and these groups at the end, everything here is called the main group elements, right? So this is the main group. In case of our periodic table, these are main group elements. Whatever you see right here in the middle are called the transition elements. And these, the elements, there's always two series, which is called the lanthanide series and the actinide series. So this is lanthanum and actinide. These elements right between these two elements, we have a cutout in the periodic table, and this block right here is called the inner transition elements. So these are the inner transition, this is the transition elements or transition metals, and rest everything is the main group elements, right? So now this, what you see up on top, these are called the group numbers, right? The columns that we see are called the groups in a periodic table, and the rows are called the periods in a periodic table, correct? All right, so next thing that you guys might remember in a periodic table is about something about electronic configuration. So we'll discuss more in detail electronic configuration in a little bit, but I just want to go over the quick overview of different blocks and how they are named with respect to electronic configuration. So if you guys remember, the first two blocks are called the S block elements. These right here, again, these group between 3A to 8A are called the P block elements. This middle portion that you see, which is the transition metals, the whole middle section is called the D block elements. And this block that has been cut out from the periodic table is called the F block elements. What are these S, P, D, and F? If you remember in electronic configuration, we know that usually an atom consists of a nucleus, which consists of protons and neutrons in the middle, and around that we have different energy levels or different shells. These are called the shells, right? So each shell consists of certain number of electrons, and how do we name these shells? Each of these shells is named by a number, or sometimes or even an alphabet. It is called the principal quantum number, right? Which is n equal to 1, n equal to 2, n equal to 3. So this is like shell 1, shell 2, shell 3, right? Now that is the first part of the electronic configuration. What is the next part? Each shell consists of subshells, right? Now these subshells are what? These subshells are named as S, P, D, and F subshells. And each of these subshells consists of orbitals. And orbitals are the exact or most probable location where we can find electrons. So if you remember, we always fill out S orbital first, then we go to P, then we go to D, then we go to F. This is based on the energy level or different energy of each of these subshells or each of these orbitals, right? So based off of this group right here up front, the first two groups are called the S block. Then everything on the right is called the P block. In the middle we have D block, and then right outside, cut out from the periodic table, is the F block. So now I just want to go over one more thing while I'm at it here, and then we'll discuss electronic configuration later on. But each of these subshell we saw consist of orbitals. Now if you guys remember, S consists of how many orbitals? Only one orbital. So S is always one orbital, and each orbital is usually shown by one square, correct? Now P, how many orbitals are present in P? P consists of 3 orbitals. So we usually draw it 1, 2, and 3 squares, right? D consists of, I'll draw it right here. So D subshell consists of 5 orbitals, and it is drawn in this form. So we have 1, 2, 3, 4, 1, 2, 3, 4, and 5. So total 5 orbitals. Last is F. F subshell consists of 7 orbitals, and it's drawn with 7 squares. So 1, 2, 3, 4, 5, 6, and this is the last one. 1, 2, 3, 4, 5, 6, 7. And now the last thing that you guys probably remember is how many electrons are present in each orbital. So each orbital can maximum consist of 2 electrons, right? And those electrons are usually drawn in this form. Each of these electrons has a different spin, so they are drawn in opposite directions. So each of these arrows represents 1 electron. Each orbital can maximum consist of 2 electrons. So how many electrons can we have in S orbital? In total, we can only have 2 electrons, right? 1 times 2, 2 electrons. 3 orbitals in P consist of 3 times 2, which is 6 electrons. So we can have 1, 2, 3, and then 4, 5, and 6, right? So we can have 6 electrons here. Now another thing I want to mention here, whenever you're filling up the orbitals, if you remember, the rule is that we always put 1 electron in each of the orbital, and then if we have more electrons, that's when we start pairing the electrons, right? So you don't put 2 electrons in the first orbital. You always put 1 electron in each orbital, divide it equally, and then if you have more, you can start pairing up. So for instance, if I have d orbital, d subshell, sorry, it consists of 5 orbitals. So how many total electrons will it consist of? It can maximum contain 5 times 2, so 10 electrons in total. And if I were to draw those 10 electrons here, I would do 1, 2, 3, 4, 5. And now since I have more electrons, I'll start pairing them up, which is 6, 7, 8, 9, and 10. So that gives me total 10 electrons in d orbital. Similarly, how many electrons can we have in F? F is 7 orbitals, so it would consist of 7 times 2, meaning total of 14 electrons. So if you were to draw it again, always draw 1 electron in each of them. 1, 2, 3, 4, 5, 6, 7. And now if I have more, I'll do 8, 9, 10, 11, 12, 13, 14. And how do you know how many electrons anything consists of? That would depend on which element we are talking about. So whatever element, let's say, whichever element you pick, however many electrons it consists of in that particular subshell, that's what would decide how many electrons you draw in the orbital diagram. So that is like a brief overview, okay, of what are the shells, what are subshells, what are orbitals, how many electrons are present in each of the subshells. Okay, we'll come back to this electronic configuration in a little bit, but first let's go back to our actual discussion of transition elements and inner transition elements. Okay, so let's see what are some properties of these transition metals. They are, first of all, they're all metallic. That's why they're called transition metals or transition elements. Okay, and how about these transition metals? All of them are metal, whereas the main group elements, like I showed you before, they can consist of metals and non-metals. So if you remember in the periodic table, whatever's on the left is metallic, and as you go more towards the right side of the periodic table, things start turning into non-metals or non-metallic character, or metallic character essentially reduces as we go from left to right, right? Now you'll see, and it will make more sense later on, that most of the transition metals compounds are usually colored, okay, and they are paramagnetic. So colored is easy to understand, that they have a distinct color to them. What does paramagnetic mean? Paramagnetic mean they are slightly attracted to a magnet. They are slightly magnetic in nature. So if you bring a magnet next to it, or if you apply a magnetic field to these metals, they will slightly behave or slightly be attracted towards a magnet. That is paramagnetic. Whereas the other elements, most of the elements in the main group are colorless and they are diamagnetic. Diamagnetic means they are not attracted to magnets. They do not have any response towards magnetic field. They do not have any attraction towards magnet. And what makes something paramagnetic? So when you write the orbital diagram of an element, if there are any unpaired electron, let's say I'm distributing electron, I have 1 and 2 electrons, that's all. So what do I have here? They're not paired. If there are unpaired electrons, that makes anything paramagnetic. So paramagnetic means unpaired electrons. If all the electrons are paired, for instance, if I draw an orbital which has 6 electrons, p, so I draw 1, 2, 3, 4, 5, 6. Everything's paired, so how many unpaired electron does it have? 0. 0 unpaired. So if it is no unpaired electrons, it means it is diamagnetic. Okay, so it has no response towards magnet. Similarly, if I have 5 electrons in a p shell, let's say, so I have 1, 2, 3, 4, 5. There's one unpaired electron. Even if there's one unpaired electron, that would make this compound or element, whatever we are talking about, a paramagnetic element. Okay. Okay, now these, like I said, we will be discussing a lot about electronic configuration. Why? Because most of the chemical and physical properties of these transition metals and its compound are all dependent on their electronic configuration, which means how many electrons do they have in their outermost subshell? How many electrons is it willing to donate? Remember, metals always donate electrons, right? Metals always form cations. They always like to donate their electrons. So how many electrons is it willing to donate? That would control how it interacts with other chemicals, and that is essentially what dictates its physical and chemical properties. For instance, you can see right here it is showing you some of the images for period 4 transition metals. So these are all metallic in nature, and you can see they have very different colors from each other. And that shows you that these transition metals, they can behave very different from each other, and everything that you see, physical properties or chemical properties, are very different from each other, and that depends on their electronic configuration. I mean, they are not very different from each other, but they are slightly different from the rest of the elements that are present in periodic table, right? Okay, so now let me come back to electronic configuration. Okay, so how do you write electronic configuration? We'll come back to transition elements later on, but let me give you a quick review. I don't want to spend too much time on this, but just a quick review. How do you find electronic configuration of an element? So remember, these are s block. How many electrons can you fill max in s? 2. This is p block, and this is d block, as the name suggests right here, and this is f block. So whenever you're starting to fill electrons, you always look for where is that element located. Okay, this group number tells you how many electrons are present in that particular element, right, in the outermost shell. And this period number, which is like here 1, 2, 3, 4, 5, 6, 7, these period number are equivalent to the number of subshell, which is the outermost, the number of shell, which is the outermost shell. So let's say if I have an atom, there's a nucleus, and then there are like a certain number of shells, right, around it. Whatever is the outermost shell, that would be its period number. The outermost would be equal to its period number. Okay. So for instance, let's say if we are writing electronic configuration of an element, for instance, right here. So let me fill this up. This is hydrogen, lithium, So let's say I'm writing electronic configuration for sodium, and here I'm only talking about the shorthand electronic configuration. So how do you write the shorthand electronic configuration? For that, you need the noble gas elements. Now remember, every single element that is present in this periodic table wants to attain the electronic configuration of its noble gas, the nearest noble gas that is possible, right? So for instance, this is neon, Ne, helium, neon, argon, krypton, and so on and so forth, right? So let's say I'm working with sodium. Then what do metals do? Metals always donate their electrons, right? Irrespective of that, whatever is the previous inert gas or noble gas that you see before that particular element, it would have the electronic configuration followed by that, right? So if I'm writing the electronic configuration for sodium, how would I write that? I start with neon. Why? Because here the atomic number I believe is 11, so it's going to follow everything like neon. So you could write 1s2, 2s2, then 2p6, then 3s1. That is the long form of electronic configuration. But if we are writing shorthand configuration, then it's going to be neon, because everything else before neon, it's going to follow whatever the configuration for neon is, right? So neon in parentheses, which is square parentheses, followed by next subshell. What is the subshell that, what is the shell number that sodium would carry? 3. That is going to be the outermost shell number, right? So we fill 3 first, and where are we here? We are right here in the S block. So it's going to be S, and which number is it? It's group number 1, so that is going to be that. It only has 1 electron, so we just fill the S orbital, right? So irrespective of where this atom is, unless it's an exception, which we tell you beforehand, most of the times you just can figure out what is the electronic configuration of an element just by looking at the location of that element in the periodic table. Okay, so let's say if I pick another example, I'm just going to pick something out of the, not from the D block. Okay, so let's say this is fluorine, chlorine, bromine. So let's say I pick chlorine. What would be the electronic configuration of chlorine? It's right here. You don't even have to think anything about this. What is the noble gas element that comes before chlorine? So all the way, if we cross back, it's going to be neon, right? So I start with neon, then I have to fill these electronic orbitals first, and then I can come back to P. So it belongs to the P block, which means it has to end with P, right? But what is the outermost shell for this? Again, it is number 3, group number 3. So I start with 3. First, if I have something over here, I have to go through the whole periodic table. Okay, so what do I begin with? I begin with S, these two. From neon, I have to come each, by counting each of these boxes, I will come to chlorine. Okay, so you have to fill each of these boxes with electrons first. So neon, then this is 3. How many S boxes will I have to cross? 1 and 2, which means 3s, 2. I'll be filling 1 electron in each of these S, 1 and 1. That makes 2. Next, I come to P orbital now, so it's going to be 3p. Again, why? Because this is shell number is 3. And how many p electrons? 1, 2, 3, 4, 5. So this is going to be 3p, 5. That's how you can write the electronic configuration of chlorine. Now you can pick whatever you want. Let's say I'm picking something from here. I'm not even going to bother what element that is right now. What would be the electronic configuration? Neon. I start filling my electrons from here, which is again 3. And I have to fill the S first, so 3s2, followed by 3p2. That's it. So that is going to be electronic configuration for this particular element. I don't know what that is. I don't care what that is. Okay, unless until it's an exception, you do care about it. But I'm just showing you this is mostly what happens when you're filling up the electronic orbitals. Okay, now we'll come to the electronic orbitals for D block and F block elements. Now, if you guys remember, whenever we come to the D block element, usually you fill the next s orbital first, then you come to D. What do I mean by that? This is how the electronic configuration would look like, Whenever we talk about d block element, you write down the electronic configuration as noble gas, followed by ns2. What is this n? Again, this n is coming from the period number 1, 2, 3, 4, 5, 6, 7. Okay, so if I pick something from here, let's say sc. Okay, this is the first transition element for us, right? So if I pick this and I ask you what is the electronic configuration, this is a d block element. First thing we know, first thing we do is noble gas. What is the noble gas that comes before this? It's argon. So again, I'm writing this electronic configuration for sc. We start with argon, right? Then it says ns2 n minus 1 dx. What is n? N can be anything between 4 and 7. Why? Because this is where the d block elements are located, between 4 period number and 7 period number, right? What is d orbital? D is filled first. You fill the s orbital, which is n, then you do d orbital, which is n minus 1. Okay, and then how many electrons do you put in d? That would vary between 1 and 10, because d orbital can have maximum of 10 electrons. So wherever this element is located, we'll fill based on that. So for instance, I'm writing sc right now, so I go with argon. Now I just carry over each box and fill it with electron. So I come to here first, which is 4. So it's going to be 4s. How many? 1, 2. Perfect. So 2, I'm going over 2 boxes, so I have to fill 2 electrons. Then I fill the d orbital. And what would be the, remember this, the quantum number, that your principal number or the shell number that you put for d is always n minus 1. So n here is 4. 4 is because of this period. So it's going to be 4 minus 1, so 3. And then you come to d, and how many positions in d am I going to? Just 1. So it would be 3d, 1. Right? So now this is the electronic configuration, the shorthand electronic configuration. If I ask you to draw the orbital diagram for just the valence shell electrons for this, how would you draw this? S would be 1 tape box, 1 orbital, D would be 5, right? So 1, 2, 3, 4, and 5. And now you can start filling electrons. So S has how many? 2. So 1, 2. Perfect. Now we go to D. D has only 1. So in one direction, I just put 1 electron. So does this carry any unpaired electron? Yes. How can I ask you a question here? I'll just ask you, can you write the electronic configuration for Sc? Which can be written out in this form. Or I can ask you, can you draw the orbital diagram for the outermost valence electrons for Sc? Then you draw this. Or I can ask you, is it paramagnetic in nature? If so, how many unpaired electrons are present in this particular element? How would you draw that? You will first have to draw the orbital diagram like this. Then you're going to distribute the electrons, and you'll see that it does have one unpaired electron, which means this is paramagnetic. Okay, let's do a couple more examples. For instance, if I'm writing configuration now for Mn, which is manganese. Okay, how would I write the configuration for Mn? Again, we'll go step by step. What is the noble gas that comes before this? Argon. So I'll put argon in square parentheses. What is the N for this? Again, it is 4. So my N is 4. 4s, usually you can just put 4s2, but I don't like to do that. I just go by the number. So you can see 1, 2, I'm filling up 2s, 2 electrons in s, so that is 2 s2. Then it is n minus 1, which is 4 minus 1, so 3, followed by d orbital, and d starts from right here. So how many boxes am I filling? 1, 2, 3, 4, 5. So how many electrons do I need in manganese in d orbital? 5. That would be the electronic configuration for manganese. So 4s2, 3d, 5. Okay, now let's say if I pick another example. Now I'll tell you everything in this periodic table. You can just start filling up the electrons like this. Anything, it doesn't matter. Molybdenum, same approach. Now, which would be the electron that comes before this if I'm doing molybdenum? What would go in square bracket? Kr, krypton right here. So put Kr. Sorry, we are doing this, right? Molybdenum. And what is the principal shell? In this case, the outermost, which is 5. So it's going to be 5s. How many do you fill? I'll have to cross these two boxes. As you cross a box, put electrons. This is s orbital, so it's going to be 5s2. Now it's going to be 5 minus 1, so 4d. How many? 1, 2, 3, 4. 4d, 4. That would be molybdenum. Okay, now there are two exceptions that I want you guys to remember. This is something you'll have to memorize. Let me put this in another color, which is Cr, not very good color. Right here, Cr, and I believe it is copper, or is it cobalt? I think it's copper, right? So we'll go with two exceptions here, which is chromium and copper. Okay, how do you write the, if it was not an exception, how would you write the electronic configuration for chromium? Let's write that down. Chromium would be, I'm filling this up, right? So what is the element that comes before this? The noble gas, argon. I'm doing chromium here. So it is argon, followed by s orbital, which is again the subshell. The shell is 4, so 4s2, 1, 2, because I'm going to cross this and this. Then I have to come to chromium, right? So it's going to be 1, 2, 3, 4. So ideally you're going to write 3d, 1, 2, 3, and 4. That's correct. But as I said, this is an exception. So what happens here? You only put one electron in s, so it's going to be 4s1, and that one electron that was taken off from s orbital will go to d. So instead of 3d4, it's going to become 3d5. So this is an exception. Chromium, why does it happen? Because the d orbital is usually more stable when it has 5 electrons rather than 4. So instead of having this 2 electrons in s, it just jumps. One of these electrons is present in d orbital, and I'll show you, we'll come to this later on the very end of this chapter to explain you how this exception works. But this is chromium. Okay, the next exception is copper. Similarly, you're going to first satisfy d orbital in case of copper. So how would we write the electronic configuration for copper? If it was not an exception, it would be copper would be, again, the element here is argon, so I'd begin with argon times, first is 4, which is again 4, 1. Let me change this color to this. Maybe not very visible, but I'll start crossing in the other direction. So 1, oops, 1, 2. So again 4s2. Oh, not very visible. 4s2. Next, I have to go fill the d orbital. So d orbital is going to be 4 minus 1, which is 3d. Now, if I just start filling, it would be 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 3d, 9. That would be my usual electronic configuration. But remember, copper is an exception. So what happens here? Again, you take one electron away from s and add it to d. So it would become 4s1 and 3d 10. Again, the reason is same. D orbitals happier when it's like all paired up rather than 4s having the 2 electrons in s. So just remember, chromium and copper are two exceptions. So whenever you're writing their electronic configuration, write the normal approach and then take one electron from the s orbital and move it to the d orbital. Okay, so that is the electronic configuration for most of these elements. Now, how can I ask you a question? Same approach. So let me ask you, how many unpaired electrons are present in copper? So you would write the electronic configuration, draw the orbital diagram. You can see in case of D, 5 orbitals, 10 electrons. All of them are going to be paired, right? But there's this one electron which is always going to be unpaired in s orbital. So it always consists of one unpaired electron, which means this is going to be again paramagnetic. All right. Okay, moving on. This was all about D block elements, okay, which is group number, period number 4, period number 5. What happens when you come to period number 6 and 7? When you come to 6 and 7, remember these are F block elements. So whenever you're writing these elements, not these are still D block. If you're writing these elements, these are F block elements. Whenever you come to F subshell, remember the electronic configuration changes to noble gas, NS2, same thing, N-2F and N-1D. So everything else is same like above, only difference now is you add an F subshell to it, and that would be N minus. How we always put N minus 1 in front of D, F is going to be N minus 2. And you start filling the electrons as normally we would do. So same thing, you just cross out each box, and as you cross a box, you fill up that particular orbital with 1 electron each. Okay. All right. So that is about electronic configuration. It's again explained right here. Now, one more thing I want to mention here. So we just wrote the electronic configuration. What if instead of giving you an element, I give you an ion? So instead of giving you just copper, if I give you copper 2 plus, how would you write the electronic configuration for that? Remember, whenever you put a plus sign, it's a cation. We are taking away electrons from there, right? So in this case, it has a 2 plus sign, meaning this would have 2 less electrons. And where do you take those electrons out of? You always take the electrons out of the outermost subshell. So for instance, right here it tells you transition metals generally form ions by losing the ns electrons before the n-1d electrons. So always take off the electrons from the s subshell, and then if you need more, you can take them off from the d subshell. Okay, so write the electronic configuration of copper first, and then take away 2 electrons, and take away those 2 electrons from s. Okay, we'll try one example now, and I will show it to you. So this right here is showing you the orbital diagram for the partial orbital diagram, which is the outermost orbital for, again, all these elements in group number or period number 4. Okay, so my suggestion to you would be that you write these or draw these orbital diagrams, figure out how many unpaired electrons are in each of these without looking at this answer. Okay, so try to do this by yourself. Just start crossing out the period, each box in the periodic table, and fill it with an electron, and that would tell you what the electronic configuration is. Okay, and practice this by yourself, and remember there are 2 exceptions. One is chromium and one is copper, and begin with that, and then you would know how many unpaired electrons are there and compare your answers here. So if you compare it and you're getting the right answers, that just means you understood the concept. Okay, and that's a very good practice. My advice would be that you don't look at the answers here and try to do it yourself. Okay, so I'll move on to some of the sample problems. So for instance, right here, the first question is asking you write the condensed electronic configuration for the following. First one is ZR, V3 plus and MO3 plus. Okay, so for this, what do we need? You just need a periodic table, and you need to remember that it's always NS2, N-1D, whatever number of electrons, and if it's something in f orbital, it is going to be N-2F. Okay, so to solve this question, we need a periodic table. So you just go to your periodic table and remember these top configuration that I showed you. Again, there's not much to memorize. Remember, there's noble gas, then it's whatever the number times s, and then n-1 d, and then you just cross each one. So let's start with the example. So right here we are doing, the first question was to work with ZR, which is right here. Atomic number is 40. So how would you write the electronic configuration for ZR? We go to the first element, whatever is before this, the noble gas, which is krypton. So it's going to be Kr in square brackets times, what is the period number here? It's 1, 2, 3, 4, 5. So this belongs to period number 5, which means it's going to be 5s2. How to cross each box? 1, 2. These are S block. So since I'm crossing out S block, I'll put the electrons in S block. And then 5 minus 1 would give me, next is d orbital, right? So right here, 5 minus 1 would give me 4d. And how many electrons in d? I cross now the d block element. So 1, 2, which means 2 electrons in the d orbital. Okay, if I ask you to draw the orbital diagram, partial, it's going to be S, which will consist of 2 electrons, so 1 and 2, followed by D, which would have 5, 1, 2, 3, 4, and 5, and it has only 2, so you put 2 electrons in 2 different orbitals. Again, don't pair them up. You first give 1 electron to each orbital and then you start pairing them up. So how many unpaired electrons are present in ZR? 2. Okay, next question was V3 plus. Okay, so if this is your question now, it's not just asking you the simple element. Remember, if there is charge, we have to consider that charge. Okay, so let's find V in our periodic table first. It's right here. Okay, so how do I do this? I would first write the electronic configuration for V, and then I'm going to take electrons off from there. Okay, so if we are just writing the configuration for V, let's start. What is the noble gas that comes before it? Argon. So we'll put argon right here, followed by the s orbital, which is again the primary or the principal shell is going to be 4. So 4, I'm going to cross 2s, so it's going to be s2. Then I come to d orbital, which is going to be n minus 1, so 4 minus 1 would give me 3. D, I cross these elements 1, 2, and 3. So it's going to be 3d, 3. Now remember, the question was not asking me for V, it's asking me V3 plus, which means I have to take 3 electrons away from here. Now where do you take the electrons away from? Remember, we always take the electrons away from the s orbital first. So s had 2, I took off those 2 electrons, so that gives me 2 electrons taken off. I need total 3 electrons taken off, which means I have to take 2 from the s and 1 will be taken off from d. So how many electrons will be left in d orbital? Just 2. It's going to be 4s0, 3d, 2. Okay, so you don't actually have to write 4s. Most of the times if the orbital is empty, you can just skip it. You can write it as argon 3d 2. But if you leave 4s0, that's okay, I understand it. But most of the times the proper way to write this is that you just take the empty electron orbital out from the configuration and you just write this. Okay, let's try the last question, which was molybdenum 3 plus. So this right here, molybdenum 3 plus. So let's first begin with molybdenum, the normal configuration, which would be, I'm going to make some space for myself and write it right here. And I'm going to erase all of this. So let's start fresh. Okay, so we are beginning with molybdenum. The question is molybdenum 3 plus. Okay, so first we are going to write the configuration for molybdenum, which is going to be right here. So where do I begin? I begin with krypton. So we put current parentheses krypton. Then I start cancelling my elements, right? So first I will be cancelling these s block elements, which is 1 and 2. What is the shell number? 5. So it's going to be 5s2. Next I cross the d orbitals right here. So d is going to be 1, 2, 3, 4. So d orbital consists of 4 electrons and number in front is going to be 5 minus 1, which is 4. So 4d, 4, 1, 2, 3, and 4 electrons. That is molybdenum. But again, the question is not asking molybdenum, it's asking 3 plus, which means I have to take 3 electrons out from this atom. So to take 3 electrons, remember we first take electrons out of s, so it's always going to be 2 electrons taken out from s. And I need one more, so I'll take off from d, which means instead of 4 now I'll have 3 electrons left here. So that would be 5s 0, 4d3, or you can write this as, let me put this 3 plus, it's going to be Kr. You don't put the S, you just start 4d3. So how many unpaired electron does this consist of? 3 unpaired electrons. Okay, so that is how you write the electronic configuration for transition elements and their ions. So the answers are also provided to you in the slide. Just make sure you try and solve it by yourself, and you can pick any example now and try to solve that. Okay. Next, this brings me to the oxidation state of transition metals. Now, what are oxidation state? If you remember, we just went over oxidation state in electrochemistry. Oxidation state refers to whatever is the oxidation number of a metal. It's easy in case of transition metals. In this case, why? Because whatever is the charge on the metal. So if I have a metal ion, whatever is the charge on the metal ion, which is usually going to be a positive charge, well, always going to be a positive charge, whatever this charge is, that is going to be the oxidation state of that particular metal. So for instance, if I have copper 2 plus, what is the oxidation state of copper here? It's 2 plus. If I have copper 3 plus, oxidation state is 3 plus. Okay, so whatever is the charge on that particular element, that is going to be its on one atom of that element. Okay, so for instance, if I have, let's say, something Hg, okay, if I have Hg2 2 plus, okay, then each of these atoms has, there are two atoms here, Hg2, right? The bottom two essentially tells you the number of atoms. So that means two atoms have a charge of 2 plus, so each of these atoms would have a charge of plus 1. So in that case, oxidation number of Hg is going to be plus 1. Okay. So whatever is the charge of each atom, that is the oxidation number. Now this is showing you that each of these transition metals can have multiple oxidation numbers. For instance, most of the times when we talk about something from main group, for instance, let's say sodium metal, sodium is always plus 1, right? Anything from group number 1 is always 1. Group number 2 is always 2. For instance, if I say magnesium, it belongs to group number 2, it's always plus 2, right? Similarly, if I pick something from the non-metal group, let's say if I say bromine, bromine belongs to group number 7, so it's always -1, right? So these are fixed. But when it comes to transition metals, which is D block or F block, they are very finicky. Their oxidation number depends on the metal, that the other compound that they're reacting with, the other atoms that are present next to it. So they can have multiple oxidation states. For instance, I just showed you copper can have two oxidation states. It can be +2, it can be +3. Actually, I don't think it's +3, it's +1. Copper +1 or copper +2. +3 was a bad example. Copper is mostly 1 or 2. Then if you have lead, again, lead is 2 plus, lead is 1 +1, right? So that depends on which atom you're talking about, which particular ion you're talking about. If I say iron, iron is +3 or iron +2. So they can have multiple electronic configuration, multiple ionic charges, multiple oxidation state. Now these are just showing you two, but there are elements that have like 7 oxidation states. So let me just show you some of those examples. For instance, like here, you can see this showing the oxidation state that exists. So for instance, Sc, it can only have either 1 or 0, which is easy because it only has one electron. If I pick something like chromium, see, chromium can have multiple oxidation states. It can be 0, it can be +1, +2, +3, +4, +5, +6. So it can have multiple oxidation states. Manganese can have maximum of 7, right? So these can essentially have 1, 2, 3, 4, 5, 6, 7, 8. It can have 8 different oxidation states. So again, each of these can have multiple oxidation state. You cannot tell just by looking at the ion. You cannot say, oh, manganese is just going to be +2. If that's not possible, unless you know what is the compound where the manganese is present, and then you will be calculating what its oxidation state is, which means you calculate how much total charge manganese atom has in that particular compound, and that would be your oxidation state. Now, like we just said before, each of these elements in transition metals, they have they can have different chemical and physical properties, different color, depending on their electronic configuration. So manganese 0, manganese plus 1, manganese plus 2, manganese plus 3, they can all have different physical and chemical properties. For instance, you can see right here, this is manganese 2 plus, where oxidation number is plus 2. This is manganese O4 2 minus, MnO4 2 minus, where oxidation number of manganese is plus 6. This is MnO4 minus, where oxidation number of Mn is plus 7. So each of these solutions you can see has a different oxidation number of Mn. It's still manganese, but they have different oxidation numbers and they have different color. Similarly, you can see right here there is V, which has oxidation number of 5. This is Cr 6. This is Mn, again 7. Each of them have different colors. So they're very different in color, different. They behave different depending on what is their electronic configuration, what is their oxidation number. Okay. And we already saw this before, that most of the transition metal ionic compounds are highly colored and paramagnetic. Why are they colored and why are they paramagnetic? Because they consist of one or more unpaired electrons. It is possible that you have a transition metal which does not have unpaired electrons. Okay, so that's how do you know if something has unpaired electrons or not? Just don't assume if this belongs to transition metal, it's going to be paramagnetic. You should try and write down the electronic configuration like I've shown you before, and then figure out if there are any unpaired electrons or not. Just don't make an assumption, okay? Depending on what their charge is, you might have something which is paramagnetic. So you just have to make sure, diamagnetic. So you just have to make sure that you are writing the complete electronic configuration of the outermost orbital. Okay. And this is showing you again some of these representative compounds, and it's showing you how they have different colors. For instance, this manganese chloride with water tetrahydride, it's white in color, but this copper sulfate is blue in color. Nickel nitrate is green in color. So they can have multiple different colors depending on how and what they are interacting with. Next, let's talk about lanthanide and actinides real quick. So lanthanide, again, these are the series which are like separated out from the periodic table. So lanthanide series, they are also called as the rare earth elements. Okay, their electronic configuration you have seen before is usually ns2, n-2f, n-1d. So now depending on again where these are located, they would have different electronic configuration. So let's try one question from here. So, oops, this shows you the solution as it is. Okay, so I just pulled up the slide so that your solution is not visible. So you can try it on your own first. So the question is, the alloy SmCO5 forms a permanent magnet because both samarium and cobalt have unpaired electrons. The question is, how many unpaired electrons are present in samarium? Z is given to you as 62. Z is again the atomic number. So the question is, how many unpaired electrons? Again, how would you find unpaired electrons? We need to write the orbital diagram for that. And for that, we need the electronic configuration. And for that, we need periodic table. So let's bring out our hand dandy periodic table back up. The question was about Sm. So let's go where the Sm is. So the question told you that Z for Sm is 62. So you can just look for the atomic number 62, and this right here is our samarium. Okay, so perfect. Now we just have to write the electronic configuration for this. Remember, the question is just asking you what is the unpaired electron in Sm. It did not say that it was an ion. So we just have to write what is Sm. Okay, so how would we go to Sm? Sm, remember all of these, all the lanthanide which is right here, this top box is after lanthanide, and everything below this, the second box that you see is right here after actinide. So where would Sm lie? Sm would essentially is just like somewhere here. You can just assume it's between this 57 and 72. Okay, So how would you start filling electrons for this? Same approach. What would be the noble gas element that lies before this? Again, remember it's right here. So the one before it is going to be xenon, right? So I begin with xenon, and then I will start filling up and crossing out these elements. So again, exact same thing. Okay, so we cross out this and this, which is which one? S orbital. So first thing we have to do is we have to find what is the principal shell number. So the outermost 1, 2, 3, 4, 5, 6. So this is going to be 6s2. Now remember, after you fill the s, it goes to f orbital. So first you have to fill this f orbital. And what is f? N minus 2. So n minus 2 is 6 minus 2, meaning 4. F. Now we find the electrons. This is 1. La is 1. And then where does it go to? It goes back to here. 1, 2, 3, 4, 5, 6. So 4f is the total number of electrons, and that's it. There is no d because we don't have any more electrons. So remember, you first fill the s, then f, then d. Again, these are some exceptions that are made. Usually when you get to the d orbital, it comes after the s orbital. If you go to the f, it comes after uh, again the s orbital. Okay, so this is an exception. That's why you see n minus 1 and d and n minus 2f. Okay, so again, the question was not the electronic configuration, it was about how many unpaired electrons. So let's fill our orbitals. First is s, which has 2 electrons, so 1 and 2. Next I have f. F has 7 orbitals, so 7 boxes. 1, 2, 3, 4, 5, 6, and 7. So total 7. I'll start filling up the electrons. Again, remember we fill 1 electron in each first. So 1, 2, I have total 6. 1, 2, 3, 4, 5, and 6. So rest, I don't have more electrons. So how many unpaired? All 6 are unpaired. So unpaired electron would be answer is 6. That's all. That's how easy the electronic configuration is. And that's what I wanted to discuss. So please make sure that you read through these slides before you start working on the next video. And we'll discuss about different coordination compounds and how these transition elements react with different elements, different compounds, different ions to form compounds, which is called coordination compounds.